Hello and welcome to the Caltech and JPL Virtual Summer School on Big Data Analytics. I'm Richard Doyle. I'm with the Information Data Science Program Office at JPL, and my colleague Dan Crichton, who's at the Center for Data Science and Technology at JPL. We're going to set a little context for you as to why JPL is interested, give you a little sense of the big data challenges that we're engaged with and the kinds of solutions we're seeking. So our objectives in this joint summer school are, there's a few objectives. First of all, we're going to be focusing on what it means to do data-intensive science well, ranging from basic programming approaches to deep computational methods for dealing with massive data, particularly distributed massive data. We're going to be focusing more on computational science than traditional computer science. If that distinction isn't clear to you yet, it will as we unfold this material. And it's going to be a very hands-on laboratory over these several days, and the content is delivered to you 100% online as a MOOC. Okay, so the first question to ask is, what is big data, and what do we do about it? Everybody talks about big data these days. It's kind of a buzzword. And for us, the challenge boils down to when traditional methods for dealing with burgeoning data sets and the fact that data sets are becoming more and more highly distributed as well as heterogeneous, traditional methods are falling short to be able to grapple directly with that kind of growth in data. And in particular, the end goal is always to extract understanding from data, and that's very much the goal within the NASA context. So some of the challenges that we're seeing, NASA ultimately is about delivering capability into very remote places like the far reaches of the solar system and bringing data back so that we can study the planets and beyond. And just like a lot of other institutions, we're seeing the challenge of the size and the number and the heterogeneity of these data sets keeps growing. And a core challenge that's beginning to rear its ugly head, so to speak, is that of the core tenet of reproducibility in doing science well. In the era of big data, everyone's dealing with vanishingly small slices of the available data, and when you have a publishable result, you want your peers to be able to reproduce that result, and that's becoming increasingly challenging in the big data era. So in the JPL and NASA context, we're hardly unique. These challenges are being recognized at the national level. In fact, there was a National Research Council activity in 2013 looking at big data challenges, and there's a publication called Frontiers in the Analysis of Massive Data. And I'm happy to report my colleague Dan Crichton is a co-author of that report. And one of the takeaways in that report is the need to look across the full end-to-end data lifecycle. That's going to be an important theme in all of our material. Okay, so here's a nice image of Curiosity landing on Mars. And I think you've all recall in just a few months ago, or a little more than a year ago, we landed Curiosity successfully on Mars, and that was a huge challenge. We did it those 7 minutes at Terra, and we were able to, and part of the challenges in doing that successfully was validating the techniques for safe landing on Mars, which involved processing lots of test data even before launch. Those challenges continue with typical Mars missions where, for example, one of our orbiters has a high-resolution instrument called HiRISE, and we typically only use 1% of the capacity of that instrument because of the difficulties of moving massive data back from remote locations like Mars. So this points up the life cycle view that makes sense to us in the context of JPL's space missions. Our life cycle starts with a spacecraft, a remote platform, which could be in the far reaches of the solar system. And getting data back, it's not only behind the traditional light time delays, but depending on the specifics of the location, the ability to move data back to Earth can be quite limited. And increasingly, we're exploring environments which are unpredictable, whether that's the surface of Mars or trying to conduct operations near a comet where the activity can be volatile. So this all translates into needs to be doing some forms of data analysis on board the spacecraft and at least prioritizing data and sometimes making decisions about how to react to data, even in the onboard context. So continuing through the life cycle view, that's what we call the flight system part of the life cycle. The data is communicated to the ground where there's various processing involved to create usable data products that then the end users, the scientists, can use. Even in the ground-based context, the massive data streams are challenging our traditional methods to keep up with the stream of data. And then finally, when the data arrives in archives, that's when the challenge really begins. We're typically seeing data arriving in multiple institutions, and the need to reconcile predictive models with these large data sets, and on and on. Now, the point about the data life cycle is that often when people talk about big data, they're really referring to what happens after the data has arrived in the archives and focusing on the massive data sets, the heterogeneity of the data, and the distributed aspect. But the point about the full life cycle view is that if you don't take that full life cycle view, you may be making choices, perhaps inadvertent choices, all the way from the collection point or through the various processing steps that occur before the data arrives in the archives. And those choices can be limiting or even compromising to the kind of understanding you'd like to extract from your data ultimately after it's arrived in the archives. So if you don't take that full life cycle view, you may have lost part of the game before you've even begun. So again, that's a point we're going to be coming back to again and again over the next several days. So this is the life cycle view that applies to space missions. It turns out there's a very similar view looking at other arenas where massive data occurs. For example, in the context of the National Cancer Institute, the so-called Early Detection Research Network, there's a pretty direct mapping between the NASA challenge and the challenges here, and that there's observational systems is the starting point for collecting data. Now, they may not be in remote parts of the solar system, but they're highly distributed. And then there's the challenge of collecting data in who knows how many different formats, and then ultimately getting into the hands of the end users, in this case the researchers for cancer research, who are interested in understanding biomarkers, and not only to be able to share their research results, but to be able to work meaningfully across these highly distributed data sets. So it's a very similar big data set of challenges, not just in NASA, but in healthcare and many other arenas. And in fact, we're seeking those solutions that can be applied cross-discipline, looking for those common principles that will work as effectively in a NASA science context as well as many other contexts. Okay, so now to expand further on this notion of the data lifecycle, here's a notional view of data from the point of collection all the way through to when it arrives in the archives. And when people talk about big data challenges, they're usually talking about some kind of a capacity shortfall that occurs in some phase of the data life cycle. So let's just pick out one of these for illustration purposes, the second on the chain on the right side, the second from the top, the one we call data triage. Sometimes your data collection source is so extreme that you have to make choices, in fact irrevocable choices, about which data you're even going to keep and store. And obviously that's an example of, if you make poor choices, that's limiting as to what you'll be able to do later in the life cycle when you're actually prepared to apply your analytics and extract understanding. So that's just a simple example, but the point here is that again, you need to take a full life cycle view to be able to be effective. Now, at this point, I'm going to hand to my colleague, Dan Crichton, who's going to give a little more introduction as to the JPL activities in the area of data science, which will lead directly into the instructional material to follow.
Very good. Thank you, Rich. So as Rich has spoken to, we really see big data as something that not only is affecting us in how we build sort of data-driven missions for NASA, but how do we address this problem, and what do we do to address and develop the techniques for being able to analyze massive amounts of data? So these are data where we need to be able to look at this life cycle, and so we're looking at the challenges across science. We're looking at other challenges in engineering, business. If you go back to that National Academy report that Rich mentioned, we see these challenges of massive data that are occurring and affecting several industries. So we need to be able to look at how do we capture well-architected and curated data repositories. This is a foundation. If you want to be able to actually do data analysis, we first have to make sure we can actually capture the data so we can begin to do that analysis. Several science areas, astronomy, earth science, planetary, ones that we're familiar with in biomedicine, have done a good job of beginning to build repositories. How do we move beyond that to begin to do the data analysis? Much of this class is going to look at techniques for being able to enable that big data analytics. Part of that is enabling the cyber infrastructure to access the data, to integrate this, to develop ways that we could look at how to analyze it using various statistical approaches. So some of my colleagues will be talking about that. Looking at the analysis and computation across highly distributed repositories. One of the challenges we have in earth science, for example, is that we collect instrument data in highly distributed repositories that would benefit from being able to be brought together. But these are different measurements that require statistical methods for data fusion, for being able to actually integrate that data. How do we develop mechanisms for being able to extract out and look for the features in the data? This is machine learning techniques that will help us to be able to look for those patterns, pull those patterns out, classify the data, be able to annotate interesting features of the data so that we can further the analysis and understanding. And then how do we look for ways in which we can compare our results against things like predictive models? This is something that's really important in areas like climate science, where we have models of climate, and we want to be able to validate those models based on actual measurements we might be making in satellites, in airborne missions, and so forth. So that's an important aspect that we really need to be able to address. And then how do we, once we've actually analyzed this data, how do we visualize it? That's part of the analysis process, but the ability to actually visualize massive amounts of data is important as well. So our colleagues during the summer school will be talking about that aspect and providing ways in which we can do analysis. One of the things that we have done at JPL is we've participated in the belief that open source technologies are important. They're a key part of how we can build the cyber infrastructure. We have developed something that we call the Object-Oriented Data Technology Framework, or ODT. It's part of the Apache Software Foundation. It provides a way to actually build this data science framework to capture, manage, and analyze data. And I encourage you to take a look at that and others that can provide this kind of a foundation. We've actually used it quite a bit in actually constructing Earth science missions, so it's flying on several Earth science missions, providing the foundation for that. We're using it on our planetary and our biomedicine, some of our work with other agencies. And so really the idea of how do you build the whole framework for being able to develop an analytics capability long term. Once you've had that framework, you want to actually be able to plug in and run the analytics. So we'll be talking about some of the techniques to do machine learning. Some of my colleagues who you'll hear from will talk about techniques in detection, prioritization of the data, classification, pattern recognition, ways in which we can look at and extract features from images. So these are capabilities that hopefully you'll get some background in by the time you finish the class. As I mentioned a moment ago, one of our big interest areas is how do we begin to look at reconciliation of climate models versus actual observations. So this is an example where a lot of that data is distributed, the model data itself, the output of those models which are running in high-performance computing centers, the observations. And so we have a real challenge of how do we actually do this in any kind of efficient way. Right now, there are cases where it might take a couple weeks to download these climate models and begin to do an experiment. As these grow, and these are growing towards the petabyte scale in the future, this challenge is only going to get worse. So how do we be able to get our arms around being able to do the analysis in some kind of efficient way? We need to be able to have techniques that help us reduce that data, particularly at the source of where that data is actually collected and managed, so that we can increase the efficiency of the analysis. In addition to what I've shown you as examples in climate and other areas, what we also find interesting is the fact that many of these techniques are not unique to earth science, astronomy. They're techniques that we can apply to other areas, such as cancer research. And so you see the ability to develop and apply algorithms for the detection of features and images. So if we're looking at pathology images or we're looking at images for cancer research, we can begin to look at trends over time. We can be able to identify features in that data that might give us insight and better understanding it. We can be able to annotate those and provide that data to discovery agents and software that can be able to help scientists be able to actually extract out and find the information they're looking for. So the computational techniques that we're going to be talking about are extremely powerful across all these various disciplines. So in summary, we'd like to welcome you to this class. We hope you enjoy it. We believe that data science, the whole area of doing what we're calling big data analytics in this class, is an area that we believe is growing. We believe it's critical that we have computationally trained scientists that are able to work along traditional scientists to be able to really change the paradigm by which we do data analysis. And that's the goal for this class, is to be able to help provide a foundation that begins to train the next generation set of computational scientists that can help us really begin to solve some of these kinds of challenges. At JPL and Caltech, we've just formed a center. We're connecting our centers together to be able to really go after these challenges. So we've got the Center for Data-Driven Discovery at Caltech. We've got the Center for Data Science and Technology. These are sister centers that we believe will be a really powerful combination that will help us as a joint entity to be able to really pursue and provide advances in research and capability in the area of computational science. So we really see the value of bringing these capabilities together. We at JPL are working with NASA and other agencies. We really believe that this is the future. So we hope you join the class, and we wish you well.